At this point in our study of integration, we've learned how to handle integrands in the form of a fraction using a couple of different techniques. One technique was to let u equal the denominator, and we recognized that the antiderivative involved a natural logarithm. Another technique was to look for patterns of sums and difference of two squares and understand that the antiderivative involved an inverse trig function. In this section, we're going to look at rational functions as integrands that don't fit either of those techniques. In section 8.5, we will apply an algebraic technique called partial fractions to the integrand to simplify it and prepare it for a simpler integration process. So, what are partial fractions? The goal of the partial fractions technique is to split complicated fractions with polynomial denominators into simpler, separate fractions that are easier to integrate. Compare the following integrals and let's discuss which techniques would be necessary to execute them both. Now, if I look at the first integral, 1 over x squared minus 5x plus 6 dx, I might consider a u substitution, u equal to the denominator. But notice du involves x to the power of 1. So in order for this to work, I would also need an x to the power of 1 in the numerator, and the integrand just doesn't have it. So that technique is out. We also might consider completing the square. We could rewrite the denominator as x squared minus 5x plus 25 over 4. That would be the value that completes the square, and I'm going to subtract it right back off. So I could rewrite that denominator as x minus 5 halves squared minus 1/4 when I combine those two terms. Now, even if we recognize the pattern here of u squared minus a constant squared, it still doesn't fit the pattern of our inverse trig function. So this would also be an unfruitful application. So the question becomes, what do we do with this one? Well, what we're going to examine is the fact that this fraction is likely the result of adding two simpler fractions together. In fact, if we look at the problem on the right, we have the integral of 1 over x minus 3, whoops, missing a dx, get a dx in there, minus the integral of 1 over x minus 2 dx. If I consider this as a separate problem, this one's very easy to integrate. We're going to make a u substitution for the denominator. We'd end up very easily with natural logs in the resulting antiderivative. Now, it just turns out that 1 over x minus 3 minus 1 over x minus 2 is 1 over x squared minus 5x plus 6. If we did the algebra, we got a common denominator, we'd find out that those are equivalent. So with the partial fractions technique, we will learn to break this cohesive fraction down into two simpler fractions. So it's like going in reverse of getting a common denominator. You've learned how to take two separate fractions and get a common denominator and combine them into a single fraction. With the partial fractions technique, we're going to break down that more complicated fraction into its simpler components. When I do that, you can see it also simplifies the integration process. So this is the technique that we'll be learning in this section.